September 19, 1940. Inside a secure conference room at the Wardman Park Hotel in Washington, D.C., a small group of American scientists and military officials gathered around a polished mahogany table, their faces etched with a mixture of skepticism and curiosity. Outside, the nation remained officially neutral, insulated from the fires consuming Europe by 3,000 miles of Atlantic Ocean. But inside that room, 6 exhausted British scientists were about to change the course of human history with a device no larger than a dinner plate. The man at the center of this gathering was Sir Henry Tizard, a distinguished physicist and chairman of Britain's Aeronautical Research Committee, whose unassuming appearance belied the extraordinary cargo he had brought across the ocean. For weeks, he and his team had traveled in absolute secrecy, first by ship to Canada and then by train to the American capital, carrying with them what one historian would later call the most valuable cargo ever brought to our shores. In Tizard's possession were blueprints, prototypes, and technical specifications representing the most closely guarded secrets of British military research, technologies that Churchill's government had spent years developing, technologies that might be the only thing standing between Britain and total defeat. At the heart of this treasure trove sat a copper and ceramic cylinder, roughly circular, with strange cavities carved into its interior. It looked unremarkable, almost primitive. Yet this object, called a resonant cavity magnetron, represented a breakthrough so profound that it would fundamentally alter the nature of modern warfare. When Tizard lifted the device from its protective case and placed it on the table before the Americans, he was offering them not just a piece of hardware, but a lifeline, and asking for one in return. To understand why Britain would share its most precious military secret with a nation not yet committed to the war, one must first comprehend the desperate circumstances facing the island kingdom in the summer and autumn of 1940. The fall of France in June had been catastrophic, leaving Britain isolated and alone against the full might of Nazi Germany. The evacuation at Dunkirk had saved hundreds of thousands of soldiers, but it had been a retreat nonetheless, and the equipment left behind on those French beaches represented years of military investment now in German hands. By July, Hitler's forces controlled the entire European coastline from Norway to Spain, and the Führer had set his sights on Operation Sea Lion, the planned invasion of Britain itself. The key to that invasion was air superiority, and throughout July and August 1940, the German Luftwaffe threw everything it had at the Royal Air Force in what would become known as the Battle of Britain. Wave after wave of German bombers and fighters crossed the English Channel, targeting airfields, radar stations, and aircraft factories. The skies above southern England became a killing ground where young pilots on both sides fought with desperate intensity, knowing that the fate of nations hung on their courage and skill. By early September, RAF Fighter Command was being pushed to its breaking point. Airfields lay in ruins, experienced pilots were dying faster than replacements could be trained, and the pressure was relentless. It was during these darkest days that Winston Churchill, the British Prime Minister who had taken office just months earlier, faced one of the most difficult decisions of his career. Britain possessed technological advantages that had already proven crucial in the Battle of Britain, most notably the chain-home radar system that allowed RAF controllers to detect incoming German raids and dispatch fighters with precision rather than flying constant patrols that exhausted pilots and wasted fuel. This radar technology, and the broader British lead in radio detection and ranging systems, represented years of secret research conducted by some of the finest scientific minds in the empire. Yet Britain's industrial capacity was strained to the breaking point. Factories were being bombed, resources were scarce, and the nation simply could not manufacture the sophisticated equipment its scientists had designed on the scale needed to fight a global war. Meanwhile, across the Atlantic, the United States possessed precisely what Britain lacked: vast industrial resources, manufacturing capability unconstrained by bombing raids, and a reservoir of scientific talent that could be mobilized to refine and improve British innovations. The strategic calculation was brutally simple. Britain could keep its secrets and face almost certain defeat, or it could gamble everything on American partnership. In July 1940, Churchill authorized what would become known as the Tizard Mission, named after the scientist who would lead it. The mission's objective was unprecedented in the history of warfare: to offer the Americans complete access to Britain's most advanced military technologies in exchange for American industrial support and scientific collaboration. But Churchill's decision was far from universally supported. Many in the British government were horrified at the prospect of handing over hard-won technological advantages to a nation that might never actually enter the war. What if the United States simply took the technology, built it for their own purposes, and left Britain to its fate? What if German spies learned of the transfer and accelerated their own research programs? The risks were enormous, and the potential for catastrophic betrayal was very real. For his part, President Franklin Roosevelt faced his own constraints. He desperately wanted to help Britain, understanding that if the island kingdom fell, Nazi Germany would control all of Europe and represent an existential threat to American security. But isolationist sentiment remained powerful in the United States in 1940, and Roosevelt had to navigate the narrow channel between doing nothing and provoking his domestic opponents into open rebellion against any foreign involvement. It was into this delicate political situation that Henry Tizard arrived in September 1940, accompanied by a carefully selected team of Britain's finest scientific and military minds. Among them was Edward George Bowen, a physicist who had worked extensively on radar development and who carried with him detailed technical knowledge of British radio detection systems. The mission traveled under conditions of absolute secrecy, with even their departure from Britain kept confidential to prevent German intelligence from learning of the transfer. The object Tizard placed on that conference table on September 19, 1940, had a history almost as dramatic as the circumstances of its delivery. The cavity magnetron had been invented just 7 months earlier, in February 1940, by two physicists working in a modest laboratory at the University of Birmingham, John Randall and Harry Boot. These men had been tasked by their professor, Mark Oliphant, with solving one of the most vexing problems in radar technology: how to generate powerful microwave signals. Early radar systems operated at relatively long wavelengths, measured in meters rather than centimeters. These long-wave systems had proven their worth in the Battle of Britain, giving British fighters enough warning to intercept German raids. But long-wavelength radar had significant limitations. The equipment was bulky, requiring large antennas and substantial power supplies that made it impossible to install in aircraft. The resolution was poor, meaning that detecting small objects like submarine periscopes or distinguishing individual aircraft in a formation was extremely difficult. And the technology that existed for generating shorter, more useful wavelengths simply did not produce enough power to be militarily useful. Randall and Boot approached the problem with fresh eyes and limited resources. Working with equipment that would have seemed primitive even by the standards of 1940, they experimented with a novel design that used a solid copper block with precisely machined cavities arranged in a circle. When electrons were forced to flow through the structure in the presence of a powerful magnetic field, something remarkable happened. The device generated microwave radiation at 10 centimeters wavelength with power levels that were orders of magnitude higher than anything previously achieved. By late February 1940, Randall and Boot had their first working prototype. By May, this experimental magnetron had been installed in a demonstration radar system that proved the concept could work in practice. The implications were staggering. With a magnetron, radar could operate at wavelengths short enough to detect small objects with precision. The equipment could be miniaturized sufficiently to fit into aircraft, allowing planes to carry their own detection systems rather than relying on ground-based stations. Navigation, bombing accuracy, and anti-submarine warfare would all be revolutionized. The General Electric Company in Wembley manufactured 12 prototype magnetrons in August 1940, incorporating refinements and improvements to the original Birmingham design. The 12th unit, a device capable of producing 10 kilowatts of microwave power, was the one that traveled with Bowen to America. It was this physical object, this assembly of copper and ceramic and carefully machined metal, that sat on the table at the Wardman Park Hotel while American scientists leaned forward to examine it more closely. The American reaction, when they finally understood what they were seeing, bordered on astonishment. Representatives from the Radio Corporation of America, Bell Laboratories, and other leading research organizations had been invited to the demonstration, and they brought with them considerable expertise in radio and electronics. When the magnetron was tested and its performance measured, the Americans realized that the British had achieved something they had thought impossible. The device was producing 100 times more power than the best American microwave generators, and it was doing so in a package small enough to hold in 2 hands. James Finney Baxter III, who would later serve as the official historian of the Office of Scientific Research and Development, wrote of that moment. When the members of the Tizard Mission brought one to America in 1940, they carried the most valuable cargo ever brought to our shores. This was not mere hyperbole. The cavity magnetron would become the foundation for virtually all Allied microwave radar development throughout the war, enabling technological capabilities that the Axis powers would never match. But the magnetron was not the only secret Tizard brought. His mission also shared information on jet engine development, proximity fuses, anti-submarine warfare techniques, and early atomic research. The breadth of the disclosure was breathtaking. Britain was essentially opening its entire arsenal of advanced military research to American scrutiny. The level of trust this required, particularly given that the United States was not yet a belligerent in the war, represented a profound act of faith in the ultimate alignment of Anglo-American interests. The American response was swift and decisive. Within weeks of the Tizard mission's arrival, the United States government authorized the establishment of a major research laboratory dedicated to microwave radar development. The site chosen was the Massachusetts Institute of Technology in Cambridge, and the new facility was given the deliberately vague name Radiation Laboratory to obscure its true purpose. This cover story suggested nuclear physics research, which was classified but not immediately relevant to radar, and it helped maintain operational security while the laboratory was being organized. The Radiation Laboratory, universally known as the Rad Lab, officially began operations in October 1940, just weeks after the Tizard mission's demonstration. It started modestly, with a small team of physicists and engineers working in improvised facilities. But it would grow with astonishing speed into one of the largest and most productive research centers of the entire war. At its peak, the Rad Lab employed nearly 4,000 people from every scientific discipline, working on multiple continents to develop, refine, and deploy radar systems based on the cavity magnetron. The work proceeded with desperate urgency. Britain was still fighting for survival, and every day that passed without improved radar capabilities meant more ships sunk, more bombers lost, and more territory ceded to Axis forces. The scientists at the Rad Lab worked punishing hours, driven by the knowledge that their work had immediate life-or-death consequences for soldiers, sailors, and airmen in combat. Isidore Rabi, one of the Rad Lab's directors and a Nobel Prize-winning physicist, later remarked that the scientists assembled for the project all came from the same bar, meaning that they were drawn from a tight-knit community of researchers who already knew and trusted each other. This pre-existing network of relationships allowed the laboratory to function with remarkable efficiency, as people who had collaborated on peacetime research projects now turned their attention to the brutal necessities of war. The first major application of magnetron-based radar came in airborne interception systems. By early 1941, the Rad Lab had developed radar units small enough and light enough to be installed in fighter aircraft, allowing night fighters to detect enemy bombers in complete darkness. This capability transformed air defense, making it possible to intercept raids that previously would have had free rein over their targets. For the first time, the darkness that had protected bombers became a hunting ground for defenders equipped with electronic eyes that could see through cloud and night alike. But the most crucial application of the cavity magnetron would prove to be in the desperate struggle for control of the Atlantic Ocean. By 1940, German U-boats were strangling Britain's maritime supply lines, sinking merchant ships faster than they could be replaced. The island nation depended absolutely on imports for food, fuel, and raw materials, and the U-boat campaign threatened to starve Britain into submission even if the Luftwaffe could not bomb it into defeat. Hunting submarines had always been agonizingly difficult. U-boats spent most of their time on the surface, where they could travel faster and recharge their batteries, diving only when threatened or when attacking. But detecting a submarine on the surface, particularly at night or in poor weather, was nearly impossible with visual methods alone. Early radar could detect large ships at considerable distances, but it struggled to pick out the small profile of a submarine's conning tower against the clutter of ocean waves. The cavity magnetron changed everything. Microwave radar operating at 10 centimeters or even shorter wavelengths could detect objects as small as a submarine periscope. More importantly, this radar could be installed in maritime patrol aircraft, allowing planes to hunt U-boats across vast stretches of ocean. For the first time, Submarines that had surfaced to travel or recharge could be detected from the air, even in darkness, even in fog, even in conditions where the human eye was useless. The impact on the Battle of the Atlantic was devastating for the Germans. Throughout 1941 and into 1942, Allied aircraft began locating and attacking U-boats with increasing success, but German naval intelligence could not understand how it was being done. The submarines carried detection equipment called METOX that could pick up signals from early Allied radar operating at meter wavelengths, giving U-boat commanders warning that they were being tracked. But METOX was blind to the microwave frequencies generated by magnetron-based systems. German submarines were being hunted by radar they could not detect, attacked by aircraft they never saw coming. The psychological impact on U-boat crews was profound. Submariners who had previously felt relatively safe on the surface at night now found themselves under constant threat. Any moment might bring the roar of aircraft engines, the explosion of depth charges, the scream of machine gun fire ripping through the conning tower. Survival became a matter of luck rather than skill, and the once confident U-boat service began to experience a fatalism born of technological helplessness. The Germans remained ignorant of the magnetron's existence until February 1943, when a British bomber carrying an advanced H-2S radar system crashed near Rotterdam. German scientists examined the wreckage and discovered the cavity magnetron at the heart of the radar set. The discovery triggered immediate alarm in German naval headquarters. Admiral Karl Donitz, commander of the U-boat force, finally understood why his submarines had been dying at unprecedented rates. The revelation came too late. By the time Germany comprehended the nature of the Allied technological advantage, the tide of the Atlantic battle had already turned irreversibly against them. May 1943, which came to be known as Black May in German naval circles, saw the destruction of 43 U-boats in a single month. This catastrophic loss rate, approaching 75% of boats deployed, was unsustainable. On May 24, 1943, Donitz issued orders withdrawing U-boats from the North Atlantic convoy routes, effectively conceding defeat in the campaign that had come closest to forcing Britain out of the war. Among the dead was Donitz's own son, Peter, who perished aboard U-954 in May 1943, a personal tragedy that underscored the human cost of Germany's technological disadvantage. But the cavity magnetron's impact extended far beyond submarine warfare. The Rad Lab developed more than 100 different radar systems during the war, adapted for roles ranging from anti-aircraft fire control to navigation to bombing through clouds. The H-2X system, operating at even shorter wavelengths than the original magnetron designs, allowed bombers to identify ground targets through complete cloud cover, eliminating weather as a factor that could protect industrial targets from strategic bombing. Ground-based early warning systems using magnetron technology provided detection ranges and accuracy that earlier radar could not match. Naval gunnery systems combined magnetron radar with proximity fuses, another technology shared during the Tizard Mission, to create anti-aircraft defenses of unprecedented lethality. The combination proved particularly effective against Japanese kamikaze attacks in the Pacific, where radar-directed guns could engage aircraft at ranges and with accuracy that saved countless Allied ships and lives. The Lorne navigation system, developed at the Rad Lab using principles derived from microwave technology, provided worldwide navigation capabilities that allowed aircraft to determine their position with precision regardless of weather or visibility. This system would remain in use for decades after the war, becoming the foundation for civilian aviation navigation until the advent of satellite-based GPS. The total investment in radar systems developed by the Rad Lab exceeded $1.5 billion, an astronomical sum in 1940s currency. Half of all radar deployed by Allied forces during World War II was designed at that single laboratory in Cambridge, Massachusetts, a testament to the extraordinary productivity unleashed by the combination of the cavity magnetron and American industrial and scientific resources. Yet the magnetron's legacy extended beyond its direct military applications. The intensive research conducted at the Rad Lab advanced fundamental understanding of microwave physics, electromagnetic properties of matter, and radio communication principles. When the laboratory closed on December 31, 1945, its accumulated knowledge became the foundation for MIT's Research Laboratory of Electronics, which would become one of the world's leading centers for electronics and communication research. Many of the scientists who worked on wartime radar projects would go on to distinguished careers in academia and industry, carrying with them expertise developed under the pressure of military necessity. The Tizard mission itself accomplished far more than the transfer of radar technology. It established channels of communication and trust between British and American scientific establishments that would prove crucial in other areas of wartime cooperation. The mission's discussions of jet engine development helped accelerate American work on turbojet propulsion. Information shared about atomic physics contributed to the British involvement in the Manhattan Project, the program that would ultimately produce the atomic bombs used against Japan in 1945. More broadly, the Tizard mission established a template for scientific collaboration that would outlast the war itself. The recognition that technological development required not just individual genius but also industrial capacity, institutional support, and international cooperation became a cornerstone of post-war science policy in the United States, United Kingdom, and Canada. The relationships forged in 1940 evolved into permanent arrangements for sharing research, coordinating development programs, and maintaining technological advantages over potential adversaries. In November 2015, on the 75th anniversary of the Tizard mission, representatives from the United States, United Kingdom, and Canada gathered in Washington to commemorate the event and renew their commitment to scientific cooperation. John Holdren, director of the White House Office of Science and Technology Policy, spoke of the cavity magnetron's role in tipping the balance against U-boats in the Atlantic, enabling precision anti-aircraft fire in the Pacific, and contributing to Allied victory through multiple technological pathways. Vernon Gibson, chief scientific advisor for Britain's Ministry of Defence, called the Tizard mission a desperate act of trust that sowed the seeds for future victory and collaboration. That characterization captures something essential about the decision Churchill and Tizard made in the summer of 1940. Britain was fighting for survival, outnumbered and outgunned, with its cities burning and its people wondering if invasion was imminent. In that moment of maximum peril, the British government chose to gamble everything on American partnership, sharing secrets that had taken years to develop in exchange for promises of support from a nation not yet committed to war. The act required courage, strategic vision, and a willingness to trust in shared values and common interests, even when immediate circumstances suggested caution and secrecy. The Americans, for their part, responded to that trust with remarkable energy and commitment. Even before Pearl Harbor brought the United States formally into the war in December 1941, American scientists and engineers were working around the clock to develop, refine, and produce radar systems based on British technology. The speed with which the RAD Lab was established and began producing results demonstrated American industrial and scientific capacity at its finest. Historians have long debated what would have happened if Britain had not shared the cavity magnetron with the United States. Could Germany have developed equivalent technology? The answer appears to be no, at least not on the timescale that mattered. German scientists had experimented with magnetron designs, but they had not achieved the breakthrough that Randall and Boot accomplished in February 1940. By the time German researchers examined the captured British radar in 1943, Allied forces had already deployed magnetron-based systems across every theater of war, establishing a technological superiority that Germany could not overcome. Could Britain have developed and deployed the magnetron without American help? Again, the answer seems to be no. British industrial capacity was simply too constrained by the immediate demands of wartime production and the constant threat of German bombing. The manufacturing expertise, raw materials, and industrial infrastructure needed to produce thousands of sophisticated radar systems existed in abundance in America but were desperately scarce in wartime Britain. Without American partnership, the magnetron might have remained a brilliant laboratory invention that never achieved its full military potential. What if the Tizard mission had failed? What if American officials had received the British delegation with skepticism, demanding concessions or refusing to commit resources to joint development? The Battle of the Atlantic might have lasted years longer, with German U-boats continuing to sink ships faster than they could be replaced. Strategic bombing of Germany would have been far less effective without radar navigation and bombing systems that could operate through cloud cover. Air defense against Japanese attacks in the Pacific would have been vastly more difficult without the precision that radar fire control provided. The Allies would likely still have won the war, given their advantages in population, industrial production, and resources, but victory would have been far more costly in both time and lives. The broader question is what the Tizard mission reveals about the nature of technological advantage in warfare. For centuries, military powers had guarded their secrets jealously, believing that exclusive possession of superior weapons guaranteed victory. The magnetron story suggests a different calculus. Technology by itself is insufficient. It must be combined with the capacity to produce it at scale, to deploy it effectively, to integrate it with tactics and strategy, and to continually improve it in response to enemy countermeasures. Britain possessed technological brilliance but lacked industrial capacity. America had vast manufacturing resources but was behind in certain areas of research. The genius of the Tizard mission was recognizing that these complementary strengths could be combined to create capabilities that neither nation could achieve alone. The result was not just better radar, but a model of alliance cooperation that would shape the post-war world. The personal stories of those involved in the magnetron's development add human dimension to this technological epic. John Randall and Harry Boot received just £50 each initially as a reward for their invention, a sum that seems almost insulting given the magnitude of their achievement. In 1949, they received a more substantial prize of £36,000, shared with James Sayers, who had refined their design. But the financial rewards, even when they eventually came, could never truly compensate for the knowledge that their work had saved countless lives and helped secure Allied victory. Henry Tizard himself received less recognition than he deserved for his role in forging the Anglo-American alliance. He died in 1959, having spent the post-war years in various advisory roles but never achieving the public fame accorded to military leaders or political figures. Yet his decision to propose the mission that bore his name, and his willingness to advocate for sharing Britain's most precious secrets, demonstrated strategic vision of the highest order. Edward Bowen, who carried the magnetron across the Atlantic and demonstrated it to the Americans, continued working on radar development throughout the war before returning to academic research. The physical magnetron he transported, that copper and ceramic device no larger than a dinner plate, eventually found its way into museum collections as a relic of one of the most important technological transfers in human history. For the thousands of scientists, engineers, and technicians who worked on magnetron-based radar systems, the war represented a unique moment when pure scientific research had immediate, measurable impact on life and death struggles. Many spoke afterward of the intensity of purpose that drove their work, the knowledge that every day of delay meant more casualties, more defeats, more suffering. The Rad Lab became legendary not just for its technical achievements, but for the collaborative spirit and sense of mission that characterized its culture. The cavity magnetron also had unexpected peacetime applications that its inventors could never have anticipated. The same principles that allowed the magnetron to generate powerful microwaves for radar could be adapted to heat food, leading to the development of the microwave oven. While commercial microwave cooking would not become widespread until decades after the war, the fundamental technology emerged from military research driven by the desperate necessities of 1940. Looking back from the perspective of 85 years, the Tizard mission stands as a pivotal moment in the history of World War II and in the broader history of scientific and technological cooperation. The decision to share the cavity magnetron was not inevitable. It required overcoming powerful instincts towards secrecy and control, suspicions about American intentions, and fears that the technology might be compromised or wasted. That the mission succeeded, that it led to extraordinary levels of collaboration, and that it contributed decisively to Allied victory testifies to the wisdom and courage of those who conceived and executed it. The magnetron itself, that elegant solution to the problem of generating powerful microwaves, represents a particular kind of breakthrough, the moment when theoretical understanding combines with practical engineering to create capabilities that previously seemed impossible. Randall and Boot were not the first scientists to work on magnetron designs, but they were the ones who made it work with power levels and at wavelengths that had immediate military utility. Their achievement exemplifies the role of individual creativity and persistence in technological development, even as the broader story of the magnetron demonstrates that individual breakthroughs must be supported by institutional resources and industrial capacity to achieve their full potential. The geopolitical consequences of the Tizard mission extended well beyond World War II. The patterns of cooperation established in 1940 became the foundation for NATO, for the special relationship between the United States and United Kingdom, for the Five Eyes Intelligence Alliance, and for countless other arrangements that have shaped the international order for 3/4 of a century. When British and American scientists collaborate on projects today, they are operating within frameworks that trace their origins directly to Henry Tizard's mission in September 1940. For students of military history and strategy, the magnetron story offers important lessons about the relationship between technology and warfare. Superior technology can provide decisive advantages, but only if it can be produced in sufficient quantities, deployed effectively, and integrated with sound tactics and strategy. The Germans had excellent scientists and engineers, but they never matched Allied radar capabilities because they lacked both the breakthrough of the cavity magnetron and the industrial capacity to mass-produce sophisticated electronics while fighting a multi-front war. Technology matters, but it is not the only thing that matters. The story also illustrates the dangers of technological complacency and the importance of understanding enemy capabilities. German U-boat commanders knew that Allied aircraft were finding and attacking them with inexplicable success, but German intelligence failed to grasp that the Allies possessed radar technology operating at wavelengths that German detection equipment could not perceive. This intelligence failure cost hundreds of submarines and thousands of lives, and it contributed to the ultimate failure of the campaign that came closest to forcing Britain out of the war. The human cost of technological superiority is sobering to contemplate. Every U-boat sunk by aircraft using magnetron radar represented dozens of German sailors drowned or killed in the freezing waters of the Atlantic. Every bomber shot down by radar-directed anti-aircraft fire meant airmen who would never return home. The cavity magnetron saved Allied lives by taking Axis lives, a calculus that is militarily necessary but morally troubling. The scientists who developed these systems understood that their work had this double edge, creating capabilities that protected their own forces while killing enemy personnel who were, in many cases, conscripts with little choice about their participation in the war. Yet the alternative, allowing Germany and Japan to dominate the world through military conquest, was unacceptable to those who fought against fascism. The cavity magnetron, like so many other technologies developed during World War II, served a larger moral purpose by helping to defeat regimes whose ideology was fundamentally opposed to human dignity and freedom. The technological advantages that the magnetron provided helped shorten the war, reduce casualties on all sides, and bring about the defeat of militaristic expansionism. In the end, the story of the British invention so secret that sharing it with America changed the war forever is a story about trust, cooperation, and the willingness to take extraordinary risks in desperate circumstances. When Henry Tizard placed that cavity magnetron on the table at the Wardman Park Hotel in September 1940, he was offering the Americans far more than a piece of hardware. He was offering partnership, shared purpose, and confidence that common values would ultimately triumph over immediate national interests. The Americans responded by mobilizing their scientific and industrial resources to turn a brilliant British invention into a war-winning technological advantage. The legacy of that moment endures. Every time British and American forces operate together, every time researchers from allied nations collaborate on defense technology, every time intelligence is shared in pursuit of common security objectives, the spirit of the Tizard mission lives on. The cavity magnetron itself may be obsolete, replaced by technologies that would seem magical to the scientists of 1940. But the principle that Tizard embodied, that shared knowledge and cooperative development can create capabilities impossible for any single nation, remains as relevant today as it was 85 years ago. The scientists and engineers who worked on magnetron-based radar systems could not have known in 1940 that they were helping to forge not just a military technology but a new model of international cooperation. They were focused on immediate tactical problems: detecting submarines, guiding bombers, intercepting enemy aircraft. But their work, enabled by the trust and vision displayed in the Tizard mission, contributed to something far larger than any single weapons system. It helped create the alliance that defeated fascism, established the patterns of cooperation that would shape the Cold War and beyond, and demonstrated that technological excellence combined with strategic partnership could overcome even the most daunting challenges. As the last veterans of World War II pass from living memory, the story of the cavity magnetron and the mission that brought it to America deserves to be remembered not just as a technical achievement but as an example of what nations can accomplish when they choose cooperation over isolation, trust over suspicion, and shared purpose over narrow self-interest. The device Tizard carried across the Atlantic was valuable beyond measure, But the act of sharing it was even more valuable, for it created a precedent and a relationship that would endure long after the specific technology had been superseded. September 19, 1940, was a day when the future changed in a secure conference room in Washington, when British generosity met American capacity, when a dinner plate-sized device opened pathways to victory that seemed impossible just months before. The magnetron that sat on that polished table would help turn the tide of the Atlantic battle, protect Allied ships in the Pacific, guide bombers through clouds over Germany, and save countless lives through technologies that seemed almost magical in their capabilities. But more than that, it would help forge an alliance that has endured for more than 8 decades, based on the radical proposition that in matters of survival and security, the most valuable thing a nation can share is not weapons but knowledge, not isolation but partnership, not secrets jealously guarded but capabilities jointly developed and deployed in defense of freedom.